Lesson 6.4, we are going to talk about inverse functions. So, the inverse of a relation is the set of ordered pairs obtained by switching the x-coordinates, just switching the coordinates, x and y, of each ordered pair. So here we have a relation. We can see all these x's matching up with all these y's, so we've got all those ordered pairs going on. To find the inverse, really, is just as simple as switching the x's and the y's. So this first one, the x was a 1 and the y was a 2. So now the x is a 2 and the y is a 1. On the next ordered pair, 3, 0, we do 0, 3. Then 0, negative 2. So if you just are following along, you can see that all we're doing is switching your x and your y coordinates. If you have ordered pairs, that's how you get an inverse of the ordered pairs. And of course, we're not going to work with just ordered pairs the whole time. That would be too easy. So we're going to find the inverse of equations. So here are your steps for finding the inverse of an equation. If you have f of x, go ahead and replace it with y. Step 2, switch the x and the y in the equation. Step 3, solve for y. So this first example, you can see it already has a y, so we don't need to worry about step 1. Step 2, switch the x and the y in the equation. So what that's going to look like is it's only the x and the y that switch places. So we're going to have x equals 2/3 y minus 6. And then step 3 says solve for y. So if we take this and solve for y, here's our y right here. So to get that alone, we'd start by adding 6 to both sides. So we have x plus 6 equals 2/3 y. And then how do you deal with 2/3? My favorite thing is just to multiply by the reciprocal so that cancels. I have to multiply the entire other side by the reciprocal, which is why I put parentheses around it. So this all cancels. So that does leave us with y equals, I put the y on the other side. We can go ahead and distribute this in. 3/2 x, or times x, is just 3/2 x. And then 3/2 times 6 is 9. This function is the inverse of our original function. So that wasn't too bad. Do you think we can handle one that gets a little bit trickier? Let's just look at this other example real quick. F of x equals x cubed plus 3. So we know first step, let's make this a y. And now we're going to replace the x and the y. And again, it's only the x and the y that get switched. Any exponents, multiplication, plus, minus, anything else stays the same. So we're going to have x equals y squared plus 3. And now we are going to solve for y, which means we'll start by subtracting 3 from both sides. So we have x minus 3 equals y squared. And then I'll say, all right, well, how do you undo a squared so that we can get y alone? And you'll say, oh, square root both sides. So that leaves us with y. And I'm just going to write it out front again. Now, the thing to remember is we're solving an equation, and we just square rooted both sides. We took an even root, which brings in your plus or minus. And then the square root of x minus 3, we actually cannot simplify that any further. So there we found the inverse. So just a quick note on the inverse. If you think about a graph, you have your x and your y coordinates, and I guess it's easy to see it with a parabola. Let me just throw a parabola up here real quick. If this is your function, like this, the inverse, what it actually is the reflection across this diagonal line right here. And that diagonal line is y equals x. So every point that's on your first graph, for example, oh, that got messy, of course. I'll just erase a little bit. This point, what's going to happen is it's going to get reflected across that line, and it's going to end up over there. When you switch your x and your y coordinates, that's what happens. So the inverse of that parabola is going to look like that. And you can see how it looks like a reflection across this diagonal. So visually, that's what you're doing when you find an inverse. Another thing you have to do when you talk about inverses is actually verifying that two functions are inverses of each other. So you'll be given two functions, and the question says verify that they're inverses, and we bring in compositions to do this verification. We have to do f of g of x, and then do the composition the other way, g of f of x, and if they both simplify down to just an x, then they are inverses of each other. So let me just show you what this is going to look like. First we'll do f of g of x. Why do I keep writing that the wrong way? F of g of x. So there's a composition. You can see the g function is on the inside. So we're going to take g and we're going to plug it into the f function. So we're going to have, instead of that x, here's our g function, x plus 2. And now minus 2 on the end, minus 2. And when we simplify this, I don't have anything to distribute into the parentheses, so really it's just an x plus 2 minus 2. Well, that plus 2 minus 2 cancels, so we're left with just an x. So we just showed this one, that f of g of x simplifies to just x. So let's go ahead and show the other one. If we do g of f of x, g of f of x. So again, let's take, you see how f is on the inside, so take your f function, plug it into the g function. We are going to have, here's our f function, x minus 2, and then plus 2. That's the rest of that g function right there. And then we simplify, again, nothing's being distributed in, so we can just say x minus 2 plus 2. The minus 2 plus 2 simplify, so we are left with just an x. And you can see that both compositions simplified to an x, so we'll say yes. In fact, they are inverses of each other. Alright, last idea here for your notes, and you guys better be taking wonderful notes to show me in class tomorrow. We have something called the horizontal line test. Now, if you remember, you guys already know about the vertical line test, kind of the same idea. However, the horizontal line test can be used to tell if a function's inverse will be a function without having to see the graph of the inverse. For example, let me just show you. That parabola right there, I can tell you that here's what the inverse looks like. That's the inverse. You know, if you reflect those, switch all your x and y coordinates, it's going to look like that. Will the inverse be a function? Since I'm looking at the inverse, I'll do a vertical line test. And I can see it's crossing in more than one spot, so I know the inverse is not a function. But what if I'm not exactly sure what the inverse looks like? How can I tell just by looking at the original graph? And that's where you do a horizontal line test. If you pass a horizontal line through the original function, this will tell you about the inverse without even having to graph the inverse. How great is that? So, does it pass a horizontal line test? Well, you can see you cross the graph in more than one spot, so that means that no, the inverse is not a function. So I won't actually do this one because I think there's a video for it and you guys know how to graph. Graph the function. You can see that we just threw a table of values up here. I'm pretty sure you guys can graph x minus 4, but if you're ever unsure of how to graph something, just do your table of values from -2 to 2, just like we were doing in Chapter 5. You could plug in values, get your points, and connect them. This one's going to be just linear. It's a straight line. So when you graph this, well, maybe I'll just throw it up here. It's going to look, might be a little sloppy, but something like this. Will the inverse of this graph be a function? So you do the horizontal line test to tell you about the inverse. Is it passing a horizontal line test? Sure is. So the inverse, yes, will be a function. if you wanted to graph the inverse, and especially if you had this table of values right here, if we just fill this in like this, here's the ordered pairs for that line right there. If you wanted to graph the inverse, just in case you're ever asked that, all you have to do, this is from that first slide, is switch all your coordinates. -6, -2, -1, -5, -4, 0, -3, 1, -2, 2. Now those are all ordered pairs that we can plot on our graph, and that will be the inverse of what we just did. So let's see, if we do -6, -2 is right here. -1, oh, did I do that right? -1, that seems totally wrong. Did you guys catch my mistake? I'm sure it's somewhere. Oh, look at that. So, this, I didn't even switch. It should be a -5 and then a -1. So, let's go back to the graph. -5, -1 is right here. -4 is 0. -3, 1, and -2, 2. So here's the inverse I got just by switching the x and the y coordinates. And remember what we said, that that inverse was going to be a reflection across this line right here. And doesn't it look like such a great reflection? You can see every point over here is just reflected across for the inverse. Here's the point on the function going straight across to the inverse. So that's kind of neat. There you go, graphing an inverse. 6.4. Gotta love it.